Hello, everybody. Welcome to today's lecture on model regularization. Can you hear me and see my slides?
Yes.
Very good. Thanks a lot. So today I will talk about a very important toolkit or family of techniques that allow to make your machine learning methods do much better. In particular, these methods are almost standard tools to cure overfitting, which is a main challenge or a main sickness of modern machine learning methods. The reason being that modern machine learning methods use very high dimensional hypothesis spaces. For example, if we use a linear hypothesis space or a hypothesis space consisting of linear predictor maps or hypothesis maps, then the dimension of this space is equal to the number of features that we use to characterize individual data points. And this number of features is typically astronomically large. Already when we look at data points being a snapshot taken by a smartphone, it has millions, several millions of pixels, and a standard choice for the features of an image are the red, green, blue values of pixels. So if we stack them in a vector, we get a vector of length millions. And another example for such a large or high dimensional hypothesis space is in deep learning, where we consider hypothesis spaces consisting of all maps that can be represented by a given network structure, but with tunable weights. And there are network structures, or they called deep neural networks, with billions of tunable weights. And it turns out that the dimension of the resulting hypothesis space is on the same order, billions. And I have told you at several places a rule of thumb. How many data points do we need for training a model or training a hypothesis space with a certain dimension? Does any one of you remember Alex's rule of thumb? Ten times the features. Yeah, this applies to linear regression, because in linear regression, the dimension of the hypothesis space is the number of features, but this doesn't need to be the case. In polynomial regression, we might have only one feature, but if we look at the polynomials to degree 100, the dimension is still 100. So for linear regression, the rule is 10 times the number of features, we should have training examples. But in general, we should have 10 times the dimension of the hypothesis space as training examples. And you rarely have this. So many of you are eager to use deep neural networks in the project, which is by no means required. I'm very happy if you just apply two different linear regression methods with a different set of features. That's two different models, and that's fine. But if you like, you can also use deep neural networks. Just to tell you, a deep neural network with billions of tunable parameters, to get reasonable results, you typically need billions of training data points. And you don't have this. So today we will hear some very powerful, simple, but powerful tricks. I call them tricks to still get good results by training high dimensional hypothesis spaces from a way too small training data set. And these tricks go under the name data augmentation, transfer learning, multitask learning, or semi-supervised learning. And it turns out that all of these tricks are special cases of a basic idea or a basic principle called model regularization. And today I will explain to you what model regularization is and how we can implement it. I will also demonstrate it in Excel, in an Excel spreadsheet. Okay, but first things first. Yeah, what are the three main components of machine learning? My goal in this course is that you answer these questions when I wake you up in the middle of the night, anywhere. You should be able to answer these questions. So the three components of machine learning are data as a set of data points. Each data point is characterized by typically tons of features and a label, which is the quantity of interest. Then what we do with the data, well, we fit a model to data, and in machine learning, we fit the model by choosing a hypothesis out of a hypothesis space that has, now the third component, has the smallest average loss on a training set. So here on this slide, you see how these three components are bound together. So we mix them together and cook up a machine learning method by solving this optimization problem. So machine learning, 99.9% of machine learning methods are optimization methods that solve an optimization problem, which is find the hypothesis H out of a whole space or set of hypotheses, which we call hypothesis space or model, such that the average loss on a set of data points, which we then call training set, is as small as possible. That's what I mean by machine learning in this course. That's a very pragmatic definition, but you cover a lot of machine learning theory and methods by sticking to this definition. Okay, so we have two main ingredients, I would say, of a machine learning method are data and model, because the loss function is typically something that you do not mess or ponder around too much. Either your customer, so the one who wants a machine learning method to predict something like user preference, or what is the reason that customers leave. So the final customer of your machine learning method tells you what the loss function is. So I want to know with as high accuracy as possible the percentage that a specific customer leaves. Then you use the squared error loss. Or you want to classify an image into cat or dog, and then you use the 0-1 loss to measure the quality of a prediction. So if the prediction is cat, but the actual image shows a dog, then the loss is 1. But if the prediction is cat and the actual image is cat, then the loss is 0. So this is another example of a loss function. But in general, the loss function is not something where we try out too much. Where we try out more is with the first two components, data, in particular training data, and the model or hypothesis space. And there are a few key parameters here. So the training set is characterized by the number of data points, which I call M. So this is the number of data points in the training set. This is also referred to as sample size sometimes. In many machine learning papers or books, this is also called sample size. It's the number of data points that we use in our training set. And it's important to remember, in the training set, we only can have data points for which we know the label value. So typically, getting more training data means more work, because some expert has to evaluate data points and label them. So some human has to look at an image and check, is there a cat or a dog on the image? Then we know if it's a cat or dog image, and we can add it to the training set. So sometimes it might not be a cheap option to increase M. And we will see today that we actually can increase M artificially. This is called data augmentation. So this is one key parameter of a training set, the number of data points M. Then another key parameter of a data set is the number of features. So in this course, we typically consider data points that are characterized by numeric features, and not only one single feature, but N, the number of features N. So these two parameters describe the training set to some extent already for us. Then we have another component of machine learning is the hypothesis space. This is the set of possible hypothesis functions that I consider. So one model could be linear hypothesis maps. So then the hypothesis space is the set of all of the entirety of linear maps. Or I say I want to consider as model a decision tree. Then the hypothesis space is the set of all functions that can be represented by flowcharts that we call a decision tree. So different models mean different sets or spaces of hypothesis maps. And there are tons of different models. And it's often the case that we don't know in the beginning what is the best model. So we need to try out different models and then compare them by the validation error, as we discussed in the last lecture on model selection. But today I will show you another approach to change the model, and in a smooth or continuous way. So we'll see that regularization allows to shrink or blow up the hypothesis space in a continuous fashion. And for this, to make this more precise, we need to measure the size of a hypothesis space. And I use a very simple form or a simple concept in my book to measure the size, which is called the effective dimension D. So we have parameters that characterize the size of the training set, M, the number of data points in the training set, and we have a number of features which characterize the training set, and then we have the effective dimension, which characterizes the size of the hypothesis space. And it turns out that often in many settings you can already guess if overfitting will happen. So if machine learning methods will fail to deliver a good hypothesis, and this is the case if the method overfits, you can tell this already by looking at these numbers. In particular, if the ratio of effective dimension D to the number of data points in the training set is much larger than 1, there's a very high risk that you will overfit. So I have shown here in a simple plot, we see here the validation error that we get for different models and different training sets as a function of the ratio effective dimension D. So this D is the size of the model, and this M is the size of the training set, or the number of different data points in the training set. And as soon as this ratio goes above 1, which I call the critical value, there's a very high chance that you will overfit. So the validation error goes up, but very unintuitively, the training error becomes 0. And actually, this is the very definition of this effective dimension, is that this is the number of data points that such that you will find for sure one hypothesis in that space of dimension D that perfectly fits these data points, in particular, this training set. So as soon as D is larger than M, then you will for sure always find a hypothesis that perfectly fits M data points, and the training error then becomes 0, of course. But the training error is 0, but the validation error goes up. And the validation error is the important quantity, because this is our indicator for how well is the hypothesis doing outside the training set. And in the end, we are interested in a hypothesis that predicts well outside the training set, because the training set is only used for our purposes to train a model. We then apply the hypothesis in the real life outside the training set. And for this, we need to have a good performance, the validation error should be small. So there is some sweet spot here where the validation error is minimum. And we want to reach this sweet spot by navigating on this axis here, so D over M. And we can use regularization methods to move along this axis here smoothly, so not discrete, as when we choose between, for example, linear regression using three features would be here, and linear regression using 20 features would be here. So this I mean with this I call hard model selection, so either 3 or 20. But regularization is a smooth way to change the model dimension. So we can also get values in between 3 and 4. So there is no discrete structure in the model selection process when we use regularization. And this is sometimes very convenient. Okay, so let's now discuss 2 complementary approaches to get this ratio D to M, so the size of the hypothesis space divided by the size of the training set. We must get this below 1. And there are, of course, 2 options for this. The first option is increase the training set. So how can we increase the training set? Well, we could collect more data, but as I told you, getting more labeled data points might not be a good option because it's costly. Labeling data points might need human labor, human work time. You can buy this work time, by the way, at something called Amazon Mechanical Turk. So there are marketplaces for labeling time. But it costs. So for each hour, for somebody labeling your images, you have to pay a certain fee, 10 euros, say. So you might not want to spend this. So a cheaper way is called data augmentation. A cheaper way to get more data without having somebody to label data points. And the idea is as follows. We often, in a real world application or many applications, we have some invariances in the data, or I call them also symmetries. For example, when we want to predict the maximum daytime temperature, y, based on the minimum daytime temperature, then this prediction should not depend too much on the minimum daytime temperature. For example, let's say I have a day with minimum daytime temperature -10. Then the prediction for this day should not be significantly different for another day where the minimum daytime temperature is a bit different, like -10.2. So what I typically want is that the predicted labels stay the same if I wiggle a bit around the data points by perturbing the features. And by perturbing the features, I can create new copies of a data point. So these orange data points, they are obtained by wiggling around a bit the feature values of the original data points, which are blue here. And this is called data augmentation. So I add a bit noise, I add small perturbations to the features, and say, but the label should not change. So if I have observed such a day with minimum temperature, let's say -5 and maximum temperature -3, then I could also have likely observed a day with minimum temperature -4.8, but the same maximum temperature -3. Or I could also equally reasonably or with high probability have observed a day with minimum temperature -5.2 and the same label value or maximum temperature -3. So I enforce this stability with respect to small perturbations in the features by adding or augmenting the original data set by these copies. And now all of a sudden I made a new data set of size 3 times the original set. So the original data points were the blue dots, 3 of them. And now all of a sudden I have 9 data points. So I multiply or increase the data set, increase this number m by a factor of 3. Yeah. Another example to augment data is to use symmetries in images. For example, a cat image. So if you want to build a hypothesis that predicts if an image shows a cat or not, then this hypothesis should output the same label, cat or no cat, if you rotate the image. So for each image for which you know that this is a cat image, so let's say this is a labeled data point, so we know this is a cat image, we can create 3 other labeled data points by rotating this image, but we still know this is a cat image. And so on and so forth. So we have, again, a 3-fold original data set. So there's one question. Wouldn't data augmentation decrease the machine learning accuracy? That's a good question. And this depends on the true relation between features and labels. So this depends on the actual data set, so on the statistics of the data set. But you could also say that this is a property you want the predictor to have. So you want to learn a hypothesis that doesn't change the prediction too much if the feature is, instead of -5, -4.8. So with this data augmentation, you kind of you enforce some robustness in the hypothesis, and this might actually be desirable. But of course, if you overdo, the important question is then how much we can tolerate. Can we tolerate even say if we have a perturbed data point with minimum daytime temperature +3, and is this still reasonable to have such a data point with maximum daytime temperature -3? So at some point we overdo. And then of course the resulting accuracy will be decreasing. yes, so there are coming again hyperparameters with this data augmentation. So here a hyperparameter would be how much error level do I use for creating these perturbed data points. And this is a hyperparameter, let's call this epsilon. And one way to choose between different values for hyperparameters is to try out like two values, let's say 0.5. And then we do another machine learning method, which uses data augmentation with epsilon 0.2. We learn some hypotheses for both cases, or for these different augmented data sets, and then compare based on the validation set. So this is then handled by any method that can be used to tune hyperparameters. Okay. Yeah, then not only rotation is a symmetry for this cat detector, also if we flip the image. So if we flip the image upside down or from left to right, a cat image is still a cat image. Or if we shift the cat a bit to the right top or down or left, all these shifted images are still cat images. So you see that you can create a lot of copies, or you can create a lot of augmented data points for which you know the label, because these transformations don't change the label, but they are different data points. This image is different from this image. So you have two different data points here, but they have the same label. So you have new labeled data points. Okay, so this is called data augmentation, and this is a very neat tool when you have too little data. So maybe let's illustrate this in Excel. We can do data augmentation in a spreadsheet. I will show you now how. So I have downloaded data again from the Finnish Meteorological Institute, and these were daily observations. So each day corresponds to one data point. Let me make this a bit larger. So each day here is one data point. The feature of a data point is the minimum degree, the minimum daytime temperature, and the label is the maximum daytime temperature. Yeah, can everybody see my spreadsheet?
Yes.
Thanks. So then I pick a subset of these data points, copied it here. So this is a subset of data points. Each row corresponds to one data point with label value and feature value. And then what I did, I created a model. So a model in the form of a linear hypothesis space. So I say I predict the label by computing the powers of the feature. So here's the original feature in cell B2. Then I take the power B2 to the power of 2. Then I take the, let me see if I can make this larger, the font on the screen. No. So B2 to the power of 2, B2 to the power of 3, and so on and so forth. And I weight, or I multiply these powers by these weights here. So these are the tunable parameters I use for my model. W1, W2, W3, W4, W5, W6. So these are 6 tunable parameters. So if we would now tune these weights to minimize the training error, which I have shown here. Yeah, the training error here is the sum of squared errors. I use the squared error loss, which is the difference between the true label and the predicted label to the power of 2. For each data point, I sum them up and get this way I get the training error. So now, what do you think when I tune these weights? How small can I make the training error when I choose the weights optimally as to minimize the training error on these 4 data points? 0, yes. Why can I make it 0? I have 6 tunable parameters and I have 4 data points. And Alex's rule of thumb, always have 10 times more data points in the training set than tunable parameters for your model. And this is clearly violated here. So there's one question: how do you know how many powers weights are necessary? I don't know. I just tried. So machine learning in practice is an iterative process, which is come up with a model like all the powers till the power of 6 in this case. Look how well it is doing. So make a prediction, compare the predictions with the observations, compute the loss, and if the loss is too high, change the model. So my starting point, my initial guess was powers up to 6, but I have no further reason for that because I'm not a methodological expert. If you're a methodological expert, you might say this is completely nonsense up to power of 6. I'm just a machine learning guy. So I just use a model to start with. So, okay, but now let's now test if the training error can be really made 0. So what I want to minimize is the training error. And I want to minimize the training error by tuning the weights here. Yes, I've chosen this. So let's see how far we can go. Solve. Yes, so this is 0. This is 10 to the power of minus 6. This is basically numerical rounding errors going on here. That's why it's not exactly 0, but we can assume this is 0. So, and actually here the loss for each data point is almost 0. Yeah, because the predicted label here is 3, true label is 3. Predicted label for this data point is 3.6, true label 3.6, and so on and so forth. So we make perfect predictions on the training set. We perfectly predict the training set. However, never stop here. Never ever stop looking at the training error after you have trained a model. This is a highly biased performance indicator because you trained a model to make the training error small. So you must look at some validation sets. And here I have grabbed some other data points from my raw data and I try out these weights that I have trained here on the training set. I held now fixed and try out on the validation set. And here we see, oh, here is a lot of error, particularly here. Here's the squared error 702. And this tells us that what is happening. How do we call this behavior of a machine learning method? It delivers a hypothesis. Overfitting. Yes, that's overfitting. And this is the evil in machine learning for us. We want to avoid, we want to fight overfitting. And regularization is our sword to fight overfitting. So one example of regularization I will show you later is data augmentation. So what I told about data augmentation is exactly what regularization is doing. But let me now show you by hand data augmentation. So what do? I take original raw data points. I take some raw data points. So let's say this last 3-1. I take them, I copy them, and I change a bit the feature values. So I wiggle around, I perturb now a bit the feature values, 2.6, and let's make this 1.15, and let's make this 0.55. So I have new data points. I have augmented my original data set by 3 new data sets. Out of the blue, I have created 3 new labeled data points. So, but now we have also to copy the predictor. And let's now train again. What do you think? Will we again be able to make the training error almost 0 with this new augmented data set? Probably. Any other guesses? We now have 1, 2, 3, 4, 5, 6, 7 data points. And how many tunable parameters do we have? 1, 2, 3, 4, 5, 6. So more data points than tunable parameters. So there might be a chance that we cannot overfit anymore. Let's see if this is true. Yeah, it might still be small, but maybe not that small. Okay, I forgot. I need to update. Yeah, it's not so convenient to do machine learning in Excel. It's possible, but it's not very convenient because I need to update here the training set for the computation of the training error. So let's do it again. Solve. Naja, so 10 to the power of -3, still small, but by a factor 1,000 larger than before. So we cured a bit overfitting. What could we do now? Well, do more augmentation. Just copy again. Or let's say 3, that it fits here nicely. 3, and wiggle around a bit on the feature values, leaving the label values untouched. So. Yeah, you can find this spreadsheet on the My Courses page under section lectures. So let's update the sum here again for the training error. We need all of them. Let's solve. So we now increase the training error by a factor of 10 still. So still overfitting, but even less than before. So you could guess that we could add even more augmented data. So let's see what happens on the validation set. And here we had an extremely large error before, 600. So it seems now on the validation set, the performance became better. So we improved the performance on the validation set, and this is actually what we want. So we increased the training set, the training error, but we bought ourselves. So we invested increasing the training error, but this bought us a reduction in the validation error, and this is what we wanted. So this is what we did now was we added data. So I want to show this in the slides, how we navigate it. So we increased data by augmentation. So we made this M here, we made this M larger, which means we moved to the left. So we moved a bit to the left. We started out here in the overfitting regime. With 0 training error, but very large validation error. And then I increased the number of data points in the training set. So I made the M larger, which means this ratio becomes smaller. So I moved a bit to the left, which means the training error increased, but I got the validation error down. And then, of course, it's then a matter of patience to continue this and try, if it's possible, to get the validation error even more down and find this sweet spot beyond or to the left. Then this validation error goes up again. Okay. So this is how you can navigate this curve and minimize the validation error using data augmentation. Okay, there was now one question. How do you know that the method was overfitting and not that there was just an outlier in the training set? I don't know. I don't know. So it's just, again, I start out with a model. My model is also a kind of a higher level model, is that these data points are all from the same distribution. So they are independent and identically distributed. This is my first model. I could test or try to find out if this model is not good and I should model outliers. But I don't do this. So this would be a possibility to try to first analyze the data points that you have and see if it's reasonable to assume that there are few outliers. But I don't consider this. This is another possible model you could try out.
One question here.
Yes.
You're now using the training error here to optimize the model, but could you just use validation error directly and solve for minimum validation error here in this case?
Well, if I would use the validation error to tune the weights, then the validation set becomes the training error.
Yeah, I don't really know how to paraphrase this question too well, but
yes, I think I know what you mean, because I have here so many validation data points. Why don't I use them also for training?
No. What I mean is, can you? Well, I don't actually quite know how to put it, but I need to think a little bit more. I'll ask in the chat in a second.
Yes. Okay, then another question, independent of if there are outliers, more data solves that problem as well. Yeah, more data also helps if you have outliers, because then you might be able to better spot the outliers. Yes, but as I said, in our simple model here, we don't consider outliers. We don't consider them. Another question, which is better, increasing the size of the data set or decreasing the effective dimension? That's a very good question, and I don't have a definite answer for that. It depends how easy or how convenient it is to create augmented data. So this data augmentation uses symmetries, and if you're really sure about symmetries in your application, one of the best examples for such symmetries is rotations of images. When you look at the rotated image of a cow, it's still a cow. Other example of symmetries that come up and are very well understood that they are actually there is in physics. When you have a physical experiment, or you look at some physical system, or like a semiconductor, then the semiconductor behaves typically the same at a certain time as 2 hours later. So you can then consider this time evolution as providing new data, augmented data. Or an apple falling down a tree should fall down the same way in Finland as in Austria. So there's a symmetry regarding the space coordinates of a physical event. So you want typically your systems to be invariant to simple transformations like moving the system around. And these symmetries, they can be exploited in machine learning by creating artificial data points, where you just artificially do as if you have moved the system a bit spatially or in time. And yeah, so if you have a good understanding of the symmetries, then data augmentation might be preferable. But if you don't know a lot of good symmetries in your system, then regularization might be more promising. So it's hard to say in general what is the better approach. And we will see in a second actually that regularization is doing data augmentation in a specific way. So when you do regularization, you implicitly do data augmentation. So actually, data augmentation and regularization is the same thing. But yeah, let's now have a little break of 5 minutes, and let's get back to regularization at 5 p.m. Okay, so welcome back. Let's now continue with the other approach to bring down the ratio between the size of the hypothesis space and the number of training data points below the critical value 1. So first we considered data augmentation, which tried to increase the number of data points in the training set. Now we try to decrease the effective dimension or the size of the hypothesis space. And how do we do this in regularization? Well, the idea is to replace the original hypothesis space. So this is the original learning problem. we choose a model like decision trees or neural networks or linear predictors, which corresponds to a certain set of hypotheses, calligraphic age. And we then look for training means to solve this minimization problem. So we look for the hypothesis that incurs the minimum average loss on the training set. So as we said, if the model is too large, has a too large effective degree, the resulting hypothesis will not be a good hypothesis. It will overfit the training data. So what can we do? Well, we can try to make this hypothesis space smaller, to prune it. I call it pruning. So we cut out certain parts of it and make it a smaller hypothesis space, calligraphic age head. And then we do machine learning, or we solve this training problem on the smaller over the smaller hypothesis space. So do you remember how we did this for model selection? So when we considered linear predictors with many features, how did we make the hypothesis space smaller then? How did I reduce the overfitting problem in, or solve the overfitting problem in the Monday's lecture when we considered different linear regression methods? How could I make the model smaller when using linear predictors? Reduce the number of weights, which means, yeah, reduce the number of features. So feature selection is one way to make the hypothesis space smaller, because we effectively set the weights of all features that are not used anymore to 0. And this means we only consider as a subset of the linear predictors. So this is one way. But now, or another example is if you use polynomial regression, you reduce the degree of the polynomial. So instead of a degree 3 polynomial, you use only degree 2 polynomials. That's another example for how to make a hypothesis space smaller. Yet another example is called early stopping. So this goes a bit beyond this course, and it's more relevant for deep learning. But the idea is that you make the search space. So when you solve this learning problem, what machine learning algorithms do is they search over this hypothesis space. And when you reduce this search space, you kind of restrict your learning to a smaller subset. And this is exactly what is done by early stopping. So you can say when you run an algorithm 10 iteration, it explores this area of the overall hypothesis space. So you reduce the effective hypothesis space to this subset here. If you use 100 iterations, you explore a bit more, but still not the whole space. And then if you use 10,000 iterations, you explore the whole hypothesis space. So by early stopping an iterative algorithm, for example, gradient descent is one such algorithm, you reduce the hypothesis space effectively. But here in regularization, we do it by a different approach. We reduce the hypothesis space by adding a regularization term to the training error. So instead of minimizing only this training error, the average loss on the training set, so this, okay, I have to stop quickly. So instead of minimizing only this training error here, we minimize the training error plus an additive term, which we call regularization term. And this regularization term can be interpreted as the anticipated increase of the prediction error or loss the prediction loss, when we apply the hypothesis not on the training set, but to data points outside the training set. So this term here somehow estimates by how much larger the errors are on the validation set compared to the training set. When we look back at the spreadsheet, so here we have the loss on the training set. This is the first component in this formula I showed you. This is the training error, and this is quite small. But then on the validation set outside the training data, the loss is much larger. And the question is, can we somehow guess this already by looking at these weights? And it sounds strange and almost unbelievable, but there are ways to estimate already just from this data set and these weights, how much larger will be the loss on the validation set. It's possible, believe it or not. And this is done in regularization. So we don't minimize only the training error, but we minimize a sum of the training error, which is shown here in this formula. So I add to the training error another term, which is this regularization term, which I have defined here. And this regularization term is an estimate or guess or approximation for how much larger the loss will be on the validation set compared to the training set. And you have seen such an example of regularization already. Does any one of you remember in one of Professor Sick's lecture, he used regularization? Does anybody have an idea or a guess where this idea came already up? To not directly minimize the performance on the training set, but to minimize the performance on the training set, plus some estimate for how much worse the hypothesis H will be outside the training set. I'll give you a hint. You have seen such an approach for decision trees. So here I have digged out one snippet from Professor Sick's lectures, where to learn decision trees, you didn't look at the kind of the error rate, which is the 0-1 loss. The error rate is just the average 0-1 loss, but you minimized the 0-1 loss on the test set, on the training set, which Professor Sick called the observed error rate. So this observed error rate is the average 0-1 loss on the training set. And you don't minimize directly this observed error rate or training error, but this term plus some other term. And this other term, you can think of it as an estimate for how much larger the error rate will be outside the training set. So this is an example of a regularization term. Okay. Yeah, and I will mainly focus now on a few examples. So I will look at linear regression. Linear regression uses linear maps. So the hypothesis space is the set of all linear maps, which are weighted linear combinations of the features x1 to xn, and the weights are w1 till wn. And two popular forms for this regularization term are just the sum of squares. This is called ridge regression, or the sum of absolute values, which is then called lasso. So there was one question which I will answer before continuing. How is using regular? So the question is, how is using the regularization term different from simply adding to the training set the data points that regularization error uses? Yeah, so here, so far, I will come to that. I will discuss this in a second. But so far, this regularization term doesn't involve any data points. So this regularization term does not depend, typically does not depend on the data. So this regularization term only depends on the hypothesis. there are no data points used for this regularization term. For example, here for this ridge regression method, this uses the, as regularization term, the sum of squares of the weights. So here, when you plug this in, then there is no data. This regularization term does not depend on data at all. It only depends on the hypothesis map, or here in this case, on the weights of the hypothesis map. Yeah, I forgot to also mention or discuss this parameter lambda. This is a tunable parameter. So this is called the regularization parameter. And by making lambda large, we put a lot of emphasis on this regularization term. So we want this regularization term to be small. We want to learn a hypothesis which has a small anticipated increase of loss. Whereas if we choose this lambda small, then we put more emphasis on the training error. So for lambda 0, we reobtain standard the original learning problem, which is just to minimize the training error. Okay, and now it turns out that for most choices for the regularization term, yeah, this regularization term is a design choice. This is up to you. It depends, typically a good choice for the regularization term depends on the statistical properties of the data set. And as there are many different distributions for data, depending on the application, there's no single best choice for the regularization term. So this often also is found by or designed by trial and error. You try out the first choice for the regularization term. If this doesn't work out well, you choose another regularization term. But once you have fixed the regularization term, you can show that solving this regularized problem is equivalent to solving a standard learning problem, but on a smaller hypothesis space. So this is a new hypothesis space, which is a subset of the original hypothesis space. So we shrink the original hypothesis space to a smaller one, which is this H superscript lambda. And the shrinking, or the amount of shrinking, depends on how large we choose the lambda. If we choose lambda 0, then there's no shrinking at all, because for lambda 0, this additive term vanishes. And then, of course, this optimization problem is equivalent to this restricted problem when the restricted hypothesis space is equal to the original hypothesis space. So but in general, we don't use lambda 0. We use some non-zero value for lambda. And for non-zero values for lambda, this equivalent hypothesis space is a strict subset of the original hypothesis space. So I have illustrated this here. So this equivalent hypothesis space, calligraphic H superscript lambda, becomes smaller and smaller for increasing values of lambda. So if lambda is extremely large, then this equivalent hypothesis space essentially reduces to a single hypothesis. And the single hypothesis is the one which is the minimum of this regularization term. But this shrinking is now smooth. So it's not like discrete, choosing 5 features versus choosing 3 features, but we continuously shrink this hypothesis space. And I will now show you, so this sounds a bit abstract. I will illustrate this now again in the Excel spreadsheet, this shrinking of regularization, or the shrinking in regularization. So let's look here. So I have now chosen the sum of squares regularizer. This is called ridge regression. So here I compute the regularization term in this cell, which is just the sum of squares of the weights. This regularization term does not depend at all on any data. It just depends on the weights of the linear or of the polynomial hypothesis in this case. And now what I now optimize is not the training error itself, but the sum. So I compute the sum of the training error and the regularization term here in this cell. So now what I do is, so let's now kick out again the augmented data points. So I think these are all augmented data points. Instead of data augmentation, we now do regularization. So we have only 4 data points to train 6 tunable parameters, which would never work if we train it using the standard learning approach. But if we use regularization, it works. Okay, let's now solve this regularized problem. So we just changed the objective. Instead of only directly the training error, we minimize the training error plus the regularization term. Let's go. Okay, so what we now see is that the weights that we obtained are much smaller, and this is no surprise because by adding this regularization term, which is the sum of squares of the weights, we prefer, or we incentivize the optimization algorithm to choose weights which are smaller, which give a smaller regularization term. And this is exactly the pruning. So the larger now I choose this factor or this regularization parameter in this factor, so let's say 1000, the more the optimization algorithm is incentivized to keep the weights smaller. So we essentially reduce or shrink the hypothesis space to smaller and smaller weight vectors. So let's now again solve it, and we will see that we further reduce the size of the weights. Yeah. So we make the resulting weights become smaller and smaller, and essentially we search over a smaller and smaller subset of weight vectors, in particular those weight vectors which are sufficiently small, because any larger weight vectors, they cannot qualify for a solution of the optimization problem because the regularizer would be too large. And this is exactly what affects this soft model pruning or model shrinking. Okay, let's see what happens. The training error, if we look at the training error, is now large. Yes, because I also wanted to have a hypothesis with small weights. So it's not only the training error that counts, also the size of the weights. I have a large training error, but on the other hand, how does it look on the validation set? Well, also here quite large. So I have now both a very large training error and an even larger validation error. So it seems that I use too much regularization. So let's reduce a bit the regularization parameter and solve again. So I have reduced the training error a bit. Let's see how it does on the validation set. It's doing very poor, still overfitting to some extent. Yeah, so but I would continue now and use an even smaller regularization parameter. So what I do now by changing this regularization parameter lambda, let me go back to the slides. So by reducing the regularization parameter lambda, I make the hypothesis space larger. So I now move to the left. So I increase the hypothesis space and eventually increase the effective dimension. So what I do, I move on this validation error curve. What I had now in the Excel spreadsheet, I was here. So I had an extremely large training error and an even larger validation error. So I was here. And that's why I tried to increase the model to move to the right. So I wanted to increase the effective dimension or size of the hypothesis space in order to bring down the training error and also bring down the validation error. But I was not very happy. So I ended up somewhere here. but I still expect that there is a room for improvement. So I could even increase a bit more the effective hypothesis space, and increasing the effective hypothesis space means making the regularization parameter smaller. Yeah, so for larger values of the regularization parameter lambda, I reduce the hypothesis space. When I make the regularization parameter smaller, I increase or blow the hypothesis space up. Yes, so there's one question. Is regularization a bit like AIC or BIC? AIC and BIC are special cases of regularization which use special choices for the regularization term. Yes. Another question, can I optimize lambda by looking on the validation set error using some algorithm? Yes. So how do we choose lambda? Well, we try out different values and pick the one which results in the smallest validation error. Another question, why will the regularization help? It seems you just add another factor randomly. Well, regularization helps, first of all, when you have, so let's see what happens if I don't use any regularization. So let's say we are very unlucky and we have only 4 data points in our training set. And let's set the regularization to 0, so the regularization factor to 0, which means no regularization. Let's see what happens. So now we do no regularization. Any guesses what will happen on the training set? Training error is effectively 0, so we perfectly fit the training set. But if we look at the validation set, we get here 700, error 720. So what is happening without regularization? What happens here? Overfitting, yes. So without regularization, overfitting, but now I need, of course, I need to convince you that it could help. So let's see, we should compare, we should then of course compute the validation error as the sum of these guys here. So this is the validation error. So 730, let's see if we can get it down by increasing the regularization a bit. Let's say 1. Now we minimize, solve. Okay, this is an unlucky example because we now increased also the validation set, the validation error. Should have better chosen a better data set. So let's increase a bit more by a factor of 10. Yeah, so it seems I cannot really now prove that this helps in this case. This is a very, I would say, unlucky data set because I picked the data points by using consecutive days. So these are not really IID data points. So what I would then conclude in practice, if regularization doesn't help, so my very first assumption that these data points are IID is not valid, and I need to use methods that allow to handle or kind of non-identically distributed data. But in general, if this would be more IID data or another data set, you can see that the validation error will go down when you add regularization. So regularization helps. Yeah, it still overfits a bit, but the training error, for example, is not 0 anymore. So at least we see we are not misled by a super small training error. A high risk of overfitting is that that the users of machine learning algorithms think that they have solved the problem because the training error is 0. And this doesn't happen anymore when we regularize the method. Another question, is there a reason to use regularization if there is only one feature? Yes, because regularization helps in particular for polynomial regression. So we only have one feature, but we compute the model is a polynomial predictor. So we compute a lot of powers of this single feature. And this actually is then often challenging because of numerical properties of this optimization problem. So you might often get an error, algorithm doesn't converge in, for example, Python. In this case, in Excel, I'm not sure what algorithm they use for minimizing this training error, but also here we might have problems in actually finding the minimum training error when using polynomial regression. And this also is addressed by, or this problem is reduced or circumvented when using regularization. The numerical properties of the optimization problem also become easier, so they are easier to solve. Okay, another question. When using regularization, do we have to divide the full data set into training and validation data, or does regularization already take care of model validation? So for regularization, we don't, to implement regularization, we don't need a validation data, but we need a validation data, for example, if we want to choose between different values for the regularizer. So if we don't know what the best value for the regularizer is it 10 or 1 or 100? Well, one way to find out is to try out the different choices and look at the validation error. So as soon as we want to compare different choices for the regularization term, we need a validation set again. Yes, so this answers another question already. Yeah, so let's now continue in the lecture. Yeah, here's one good question that is related to how the lecture continues. The question is the choice of Lambda, this regularization parameter, based on the size of the weights? And this is not the case. So I choose Lambda and then see what I get out for the weights. But I will now show you that there's a nice interpretation of Lambda in terms of the feature values of the data points. So let's now go back to the slides. And this interpretation is based on the fact that regularization does a specific form implicitly of data augmentation. So it sounds a bit weird or crazy at first sight, but assume we do data augmentation and this also explains why regularization is a good idea, because so far I just have thrown at you basically the formula. So here's data augment, here's the regularized problem, just add this regularization term. From an optimization point of view, there's not much challenge here. The sum of, for example, if this is a convex function, no worries if you don't understand what convexity means, but just if you know, if this is a convex function and this is a convex function, which is often the case, then this is a convex optimization problem and can be solved efficiently. So from a computational or algorithmic point of view, there is no big challenge in regularization, but why is it good? So the first argument was that you can show that adding a regularization reduces the hypothesis space, effectively reduces the hypothesis space. And a smaller hypothesis space is less prone to overfitting. But of course, if you use a smaller hypothesis space, then this smaller hypothesis space might not contain the right hypothesis that you would need. And this happened now in my Excel demonstration. Unfortunately, I reduced the hypothesis space, so it didn't overfit. It was not able to perfectly fit the training data, but also was not able to fit the data outside. So it was just the wrong hypothesis space in the beginning. The question then is, how do we know if regularization helps, and what is a good choice for the regularization term? And I will now show you one nice link to data augmentation that might provide some help or guidance in this regard. And the idea is as follows. So assume that we do not add a few augmented data points, like if this blue data point is a cat image, then this orange would be a few rotations or shifts. Or if this blue data point is minimum and maximum daytime temperature from FMI, then we wiggle around a bit the minimum daytime temperature. We perturb a bit the minimum daytime temperature with a few numbers. No, instead, we replace each original data point by an infinite number of realizations of a random variable. So we replace each data point by a random variable. And we assume then we can draw as many realizations as we want from that random variable. For example, we could say, let's consider this blue data point as the mean of a multivariate normal random vector. And then we fix the variance. We say the variance of this multivariate normal vector is 1. Okay, so then we have specified a probability distribution. And as soon as we have a probability distribution, we can draw, by using a random generator, we can draw or generate as many realizations as we want. So we can compute as many augmented data points as we want. The important thing is that this is only a conceptual idea. We will never implement this in practice, but it turns out that when you look at the additional errors that you would get, so the squared error loss for this augmented data point and the squared error loss for this augmented data point, and if you would add them to the squared error losses you get for the original data points, then these additional losses are exactly the regularization term. So this regularization term is the additional training error you would get if you would add to each original data point an infinite number of realizations of random perturbations of this original data point. And what is nice about this link is, and this link is worked out in detail in the course book, but it's not required for completing this course. So you don't have to understand the mathematical details. But what this allows us, this link is, we can say this lambda parameter has a relation or is related to the variance of this distribution. So we can choose lambda such that this variance of these perturbations are reasonable. But we need to know what is a reasonable amount. And in some applications, we might know, for example, if these data points are obtained from sensing devices, from a temperature measurement device, then these devices typically have a data sheet which tells the temperature that this device delivers is accurate only to plus minus 0.2 degrees. And from such an information, we can say, okay, it seems we can use perturbations with a variance or standard deviations of 0.2 degrees. And this link here then tells us how to choose lambda that corresponds exactly to this standard deviation. So there's a formula. You can calculate what is the lambda corresponding to this data augmentation with a standard deviation of 0.2. So this lambda is essentially or determines the variance or standard deviation of these perturbations. Okay, so, and this also shows why regularization is a good idea, because regularization forces the learning algorithm to learn a hypothesis that is robust or that does not change too much when the data points change their features a bit, or when the feature values are perturbed by small deviations. For example, when you use regularization, then you rule out learning a function like this. So let me show learning a hypothesis that looks like this. So it jumps exactly to the few original data points, and otherwise it is constant. And such a hypothesis would result in training error 0. However, such a hypothesis, for example, would have a constant prediction for any feature value to the left here, which is not useful. And regularization, on the other hand, would kind of spot this, or would incentivize or de-incentivize to learn such a hypothesis. So using regularization would rule out to learn such a hypothesis. Yeah, how to calculate lambda from the given standard deviation. You can find this in, as I point out, in chapter 7.3 of the course book. I think it's related. Is it directly equal to the standard deviation, or I think also the variance of the features have an influence? So I don't remember exactly, but you can look it up in my course book. There's a formula. You can work it out. Okay, so as it turns out, regularization is actually the same as data augmentation. It's an implicit data augmentation by infinitely many augmented data points, which are obtained by drawing from a random generator. And the probability distribution of this random generator is related to the regularization function. So different choices for the regularization function correspond to different probability distributions. So if this distribution of the perturbed data points is Gaussian, then what you get for this regularization term is the sum of squares of the weights, which is then ridge regression. So ridge regression is doing implicitly data augmentation by drawing from a Gaussian distribution centered at each raw data point. And I'm not sure what the distribution for lasso is. So I was thinking about deriving that, but I didn't find time yet. It would be interesting to know what is the corresponding distribution for the augmented data points in lasso. Okay. So it turns out regularization is actually the same as data augmentation. So let's now briefly go over a few special cases of regularization before I start to answer all remaining questions. So first, a special case of regularization is called transfer learning. Transfer learning refers to scenarios, and these are typical scenarios when you apply deep learning methods. So you have a powerful model like a deep neural network with billions of tunable parameters, and you want to train an image classifier for your favorite dog breed. So I must admit, my favorite dog breed are border collies. I think they're just so smart. So if I want to use a deep neural network to detect border collie images, I need billions of border collie images, and I don't have so many of my dog. So what do? Well, I use existing knowledge in another deep neural network, or in the weights, in weights that have been trained or found by another machine learning problem. For example, showing detecting if an image shows a dog or not. This is a different machine learning problem from my problem, because my problem uses a different definition for the label. In my case, the label is defined by shows a border collie or not. And in this other problem too, the label is shows a dog or not. However, for this other problem, I might have many more data points for the training set. And actually even more, what is even more, somebody might have trained already a network. And you can download pre-trained network weights from the internet. And I can then use these pre-trained weights on this larger data set as a starting point for training my model, or the weights for my model, and just fine-tune them. So here again, I use a pre-trained hypothesis on a large database of dog images. And then I start from this pre-trained image. I only fine-tune it a bit. I change the weights of this model only a bit on my small data set for border collies. And this is an example of regularization, where the regularization term measures the distance of my new hypothesis from my new hypothesis to the pre-trained hypothesis. So I want to keep this distance small. I want to have the new hypothesis being close to the original hypothesis. I just want to fine tune it a bit. This is called transfer learning. And I would say this is the standard way how you use deep neural networks. You rarely train deep neural networks, or which are very large hypothesis spaces, from scratch using a random initialization for your weights. You typically always start to look around in the internet or from publications. Did anybody already train a network on a similar data set? And is this pre-trained model available? So can I download the weights? And then you download the weights and you start fine-tuning these weights on your own data set. This is called transfer learning. You will hear more about this, how to do transfer learning, by the way, in one of our follow-up courses which is deep learning with Python. And we plan to have a new edition of this course in fall. Okay, another special case of regularization is called multitask learning. Consider again the problem of learning a classifier or a hypothesis that classifies an image as shows border collie or shows no border collie. And we might have another problem. So somebody else might have another favorite dog breed, which is husky. So these are again two different problems. Problem one is detect border collies. Problem two is detect huskies. However, those two are somewhat similar because both first need to first check if an image shows a dog at all, and then distinguish between different breeds of dogs. So these are related problems, and multitask learning is a method or a bunch of techniques that allow to leverage the similarity between different learning problems. So we learn predictors for the different problems simultaneously and couple them by requiring those predictors to be similar. So we don't want this hypothesis map for detecting border collies to be completely different from the map that predicts huskies, because some features are similar. So a border collie looks more similar to a husky than to a car. So also these predictors or hypothesis maps should be somewhat similar. And this is again a special case of regularization. Here we minimize both training errors for both problems plus the regularization term, which is measuring the distance or dissimilarity between the two hypotheses. So we want those two hypotheses to be similar or the distance to be small. Yet another example of regularization is called semi-supervised learning. So again, consider the problem of classifying images if they show a border collie or not. So we have simply a too small data set for this, a too small training data set. However, we might have a massive image database with unlabeled natural images. And in semi-supervised learning, we use this big data set of unlabeled images to learn first some first map or pre-processing step, which we call feature map, to extract the most relevant features for natural images or for animal images. And we use this feature map then as a pre-processing step for a hypothesis on the smaller data set. For example, we could use the big database with unlabeled images to learn a feature map using some dimensionality reduction method. And we will hear about such methods in the next week's lectures. So we then first train this feature map using some unsupervised machine learning method on this large image database, for example, showing animals, but not specifically the animal that I'm interested in, which is a border collie. So we use this big database to first learn a feature map that extracts relevant features of an image that shows animals. And we then fine-tune on top of this feature map a linear classifier, for example, that is fine-tuned on the small data set with the border collies. And this is an example of a semi-supervised learning method. And it turns out that this is again a special case of regularization, where the regularization term here is penalizing or characterizing the ability of the feature map G to compress the unlabeled images in the big image database. So there are ways to measure the compression quality of a map for unlabeled data points. We will hear about this in the lectures on feature learning. Okay, so to wrap up, I have introduced regularization as a technique or a paradigm for soft model pruning. So we continuously reduce the model size or hypothesis space size by increasing the amount of regularization. It turns out that what we do is equivalent to a form of data augmentation using our realizations of random variables. And the distribution of these random variables corresponds exactly to the specific form of regularization term. In particular, if we use a Gaussian distribution for doing this data augmentation, this corresponds to the regularization term being the sum of squares of the weights. And then finally, I glanced quickly over 3 special cases of regularization, which are relevant for transfer learning, multitask learning, and semi-supervised learning. So this is just a glimpse of these methods. There are entire courses only on transfer learning methods. An entire course could be just on multitask learning or on semi-supervised learning. But just that you know, they are all special cases of regularization. Okay, that's all from my side. Are there any questions? Yeah, can you please repeat the question from above? Where was it? Okay, here the question is, when you try to get the validation error smaller using regularization, doesn't the validation set then kind of become another training set and therefore not a valid measure of the model's performance? Exactly. Exactly. And that's why then you need in the end always another set, which is called test set. And the test set must not have been used for training a model or for tuning any parameters like the regularization parameter. Very good point. Any other questions? Okay. Here's one. How to choose the best model based on validation error if the validation set has been used for regularization. Yeah, so I consider a regularized model as a different model. So you might compare the following models. So you have model 1 is linear regression. Model 2 is decision trees. Model 3 is regularized linear regression with lambda equal 10. Model 4 is regularized linear regression with lambda 100. And then for each of these models, you tune them by minimizing either the training error or training plus regularization term. And for each of those 4 models, after you have trained them, you compute the validation error and you pick the one with the smallest validation error. Yeah, if you have further questions on this, feel free to ask them also by email on the Zulip chat or in the exercise sessions. Another question, how does regularization work for classification? Well, in logistic regression, for example, you just have a different loss function. So you add this loss function here. So this formula here, or even before, applies to any form of loss function. So in classification problems, you have different loss functions like the logistic loss. It's exactly the same. You just add to the loss you use for a classification method, you add the regularization term. So in classification problems, you would use here for this L, you would use the 0-1 loss or the logistic loss or the hinge loss in SVM. So it's exactly the same procedure as for squared error loss. Any other questions? So here's another question, but what regularization do you use if you take, for example, the amount of legs and hair length to determine the dog breed? So you would use two numeric features, amount of legs and the hair length. And what kind of model would you use? Would you use a linear combination of those two features? Would you use linear regression or would you use polynomial? Because then you can just use this sum of squares, for example, or sum of absolute values for the lasso. Yeah, I'm not sure exactly what is meant. Please feel free to send me an email with more elaboration on that question. I'm happy to help. Okay, otherwise I will now wrap up and wish you a nice evening and see you next week on Monday when we start to talk about clustering methods. Have a nice evening.